gold medalist in MPhil Mathematics. I have been associated with askIITians as mathematics faculty for the past 3 years. So now we'll be beginning the chapter on vectors. Vectors is an extremely interesting topic, and of course it is important too from your examination point of view. I have split up this chapter into several parts, like first of all we shall begin with the meaning of vectors, of course, and then we'll be discussing the various types of vectors. Then we shall move to the triangle law of vector addition, followed by the parallelogram law of vector addition. Then we shall discuss the scalar product, that is the dot product of vectors, and then the cross product. We shall also discuss the scalar triple product and the vector triple product. And finally, we shall discuss the applications of vectors in geometry. So, in the first part, we shall begin with the meaning of vectors and the various types of vectors. So, let's begin.
Okay, so now we have a very interesting chapter, that is vectors. The chapter is extremely interesting, but yes, some of you might find it a bit difficult because the concepts like dot product and cross product are completely unknown to you. So it's just that you'll have to practice a very good number of questions, and the chapter no doubt is extremely interesting. So let's begin. So first of all, let us discuss the definition of vectors. Now if I talk of vectors, first of all, the physical quantities in general can be divided into either scalars or vectors. So we can have either scalars or we can have vector quantities. So when we talk of vectors, the first thing that should strike your mind is that it has got something to do with a particular direction. So the main concept involved in vectors is that the direction is extremely important, right? So vectors are those physical quantities which need both magnitude and direction to express them, and they obey vector rules, right? So that means they do not obey general algebra rules, ordinary algebra, right? And the examples are velocity, displacement, acceleration. See, when I talk of speed, we need not take into account its any kind of direction. So that is a scalar quantity. But when we talk of velocity, it has got to do something with direction, and so it becomes a vector quantity. Similarly, now velocity is a vector quantity. Now distance is again a scalar quantity, while displacement is a vector quantity. Acceleration is again a vector quantity. So here you can see in the figure, this denotes a vector quantity because it has got, this denotes a particular direction. So this is the magnitude, while this is denoting this direction, which is going this way. So this becomes a vector quantity. Now we'll be discussing the types of vectors, and when we talk of types of vectors, main types are equal vectors, parallel vectors, anti-parallel vectors, collinear vectors, zero vector, unit vector, coplanar vectors, free vectors, and finally position vector. So we'll be discussing each of these types one by one. First of all, we have equal vectors. And when I talk of equal vectors, it is obvious from the term itself that we are talking about equality of two vectors, right? So when are two vectors termed to be equal? Two vectors A and B are said to be equal when they have equal magnitudes and same direction. So when you talk of equality or anything about two vectors, you have to take into account the magnitude as well as the direction, right? Just keep it in mind that you have to take into account the direction also. That is the main thing. So you will call A and B two vectors to be equal when they have the same magnitude and as well as the same direction. This was quite simple, I suppose. Next we have is the collinear vectors. The word collinear is used to describe vectors which are scalar multiples of one another, right? So you will term two vectors to be collinear if they are scalar multiples of one another. These vectors are parallel. We'll be talking about parallel vectors also just now, and can have different magnitudes in the same or opposite direction. You just need to take into account that they should be scalar multiples of one another. They are parallel and can have magnitudes in the same or opposite, different magnitudes. They can have different magnitudes in the same or opposite directions, right? Now you can see it in the figure also that they can have different magnitude. Direction can be either same or they can be opposite also. Vectors A and B are collinear if A is lambda B, where lambda is a scalar. This is just a mathematical notation for they are scalar multiples of each other. So just remember, in case of collinear vectors, you need scalar multiples of each other, right? Next we have is parallel vectors. Two vectors are said to be parallel when both have same direction and one vector is scalar multiple of another vector, and that scalar is positive non-zero, right? So these vectors are parallel if they have the same direction, right? So this is A, this is B, they should be in the same direction, and one vector is scalar multiple of another vector, and the scalar should be positive non-zero. That is the main thing, right? Note, if a vector is shifted parallel to itself, there will be no change in it. Just remember this point because this is used in solving questions. These concepts are often applied in questions, right? So if you want to shift a vector parallel to itself, there will be no change in it, right? Next we have is anti-parallel vectors. Two vectors are said to be anti-parallel when both have opposite direction, right? So in case of parallel vectors, we had that they should be in same direction, but in case of anti-parallel vectors, the vectors are in opposite direction, and one vector is again a scalar multiple of another vector, but the difference is that the scalar is non-zero negative. So what do we mean by what is exactly is the difference between parallel and anti-parallel vectors? In parallel vectors, you need to have the vectors to be in the same direction. Like in fact in the figure also you can see this is my A, this is my B. So the directions are opposite and vector is scalar multiple of another vector which is non-zero negative. And this concept, that is the concept of anti-parallel vectors, is applied in subtraction of vectors. We'll be discussing the subtraction of vectors later. So this is where this concept is used. Okay, just one thing you should note here is that these definitions might not come directly, they might not be asked in your exams directly, but they are extremely important because they are applied in questions. Like I told you, this note, these things are applied in questions, and moreover, until and unless you know what exactly do we mean by a parallel vector, coplanar or collinear vectors, you won't be able to solve the questions easily. So just try to understand these definitions. Don't try to mug up, just try to understand these definitions. Next we have is a zero vector. A vector having zero magnitude and arbitrary direction. Arbitrary direction means direction is not specified, that is unknown to us. So a vector having zero magnitude and arbitrary direction is known as a zero vector. The sum of finite vector A, suppose I have a vector A and I have a zero vector. If I add up that, the sum is again the same vector A. That is quite obvious in fact. The multiplication of a zero vector by a finite number n is equal to the zero vector. That is also obvious. When you multiply a finite number n by a zero vector, magnitude is zero, so ultimately the resultant you get is a zero vector. The multiplication of a finite vector A by 0 is equal to 0 vector. So if you multiply a 0 vector with a vector A, again the resultant is a 0 vector. So this just means that in fact in this case it is obeying the ordinary algebra rules, that if a 0 vector is applied by a scalar finite number n, or you multiply a 0 vector by a vector A, the resultant is the same vector 0, right? Next we have is a unit vector. A vector divided by its magnitude is a unit vector, and a unit vector gives us a direction. What does that mean? You can write it like this, and this gives me vector A divided by its magnitude. So I get vector A as A into this, you can call it as A cap also. So this is a unit vector, that is the vector A divided by its magnitude, that gives us the unit vector. Orthogonal unit vectors, when we talk of orthogonal unit vectors, these I, J, K are called the orthogonal unit vectors. You can see it here, I is along the x-axis, J is along the y-axis and K is along the z-axis. These are called the orthogonal unit vectors. So in fact here what I can write is I cap is equal to, as we have discussed just now, vector divided by its magnitude, that is the unit vector. And similarly j is y vector divided by its magnitude, and then we have k is z vector divided by its magnitude. This also gives me x vector becomes x into I cap, y vector becomes y into j cap, and z vector becomes z into k cap. So this is about orthogonal unit vectors. In fact, you can also use, in case of, this can also be used instead of what I am using I cap, j cap, k cap. So orthogonal unit vector is just a vector divided by its magnitude, that becomes a unit vector. A unit vector is the vector divided by its magnitude. Next we have is free vectors. A vector whose value depends only on its length and direction and is independent of its position in space is called a free vector. So when we take into account only the length and direction, but the vector is independent of its position in space, that is called a free vector. And according to its definition, this is quite obvious that such a vector can be shifted parallel to itself, because its position, it is independent of its position in space, so we can just shift this vector parallel to itself. But in case a vector is associated with a given line or point, it is said to be localized in that line or that point. This is also obvious that if in case we are given that a vector is associated with a particular line or maybe a particular point, then that vector is said to be localized in that particular line or point. So this is the figure, you can see it. This is a free vector. Obviously it depends on its length and direction, but see this, if I shift this vector parallel to itself anywhere in the space, then we can do so because it is independent of its position in space. So this is a free vector. Next I have is coplanar vectors. Three or more vectors are called coplanar if they lie in the same plane. This, in fact, it is visible from the term itself. Coplanar. Coplanar means if three or more vectors lie in the same plane. Two free vectors are always coplanar, right? As we have just now discussed the concept of free vectors, from the definition it follows that two free vectors will always be coplanar. If A and B are two non-collinear vectors, then any vector R coplanar with these vectors can be uniquely expressed as R equal to XA plus YB, where X and Y are scalars, right? So what am I saying? If A and B are given to be two non-collinear vectors, collinear vectors we have just now discussed, we are saying if A and B are two non-collinear vectors, then a vector R can be expressed as XA plus YB. X and Y are scalars. I have given A and B are non-collinear. Then I can express any vector R which is coplanar with these vectors as XA plus YB, where X and Y are scalars. All collinear vectors will also be coplanar, but all coplanar will not be collinear vectors. This is an important point. Collinear, by now you must be knowing collinear vectors, we have already discussed. Now we have discussed coplanar vectors. Coplanar is when two or more vectors, three or more vectors lie in the same plane. So all collinear vectors are always coplanar, but the converse need not be true. That is, all coplanar will not be collinear vectors. Next is position vector. A vector that indicates, again it is obvious from the term itself, it follows from the term itself that it is denoting the position of a particular vector. So a vector that indicates the position of a point in a coordinate system is referred to as the position vector. Suppose we have a fixed reference point C, this is fixed reference point O, then we can specify the position of a given point P with respect to that particular point O by means of a vector having magnitude and direction represented by the directed line segment OP. This is called the position vector. What am I saying? Suppose I have a reference point, fixed reference point O, and I have a point P, then I can specify the position of that particular point P with the help of a vector having magnitude and direction, which is represented by this line segment, directed line segment in fact, OP, right? So this will be called as the position vector. So these definitions are extremely important, not because they will be directly asked in your exams, but because you need to know these concepts so that you can apply them in the question, or so that you can solve out the questions easily. Because until and unless you know what do we mean by position vector or what do we mean by free vectors, the questions will directly say a free vector satisfies such and such condition. So for that you need to know what exactly is a free vector. Just try to understand these definitions and they'll be helpful in solving out questions, right?
So I hope you must have understood the various types of vectors as well as the meaning of vectors. In the next session, we'll be switching to the triangle law and parallelogram law of vector addition. We shall also discuss the various properties of vector addition. So stay tuned.